Hello, everybody. Hello, Thomas. Thanks, thanks to be here for this Malta Academy about TLA+. So very quickly, before the beginning of this Malta Academy, I'm Clémentine. I'm working for the community team at Malt. So Malta Academy, Malt. For people who don't know what is Malt, we are a platform which is helping freelancers to find missions. So if you have any questions about freelancing Malt, and if you want to propose some topics for another Malta Academy, feel free to contact me to the email address I will put in the chat. So to let everybody connect themselves before the beginning, I will just do a quick introduction about how Malta Academies are working. So for everybody who have any questions during this webinar, feel free to put them in the questions part, just near the chat. If you don't see us, if you don't hear us, the chat is for this kind of problems. But please put your questions in the questions part, dedicated part, because it would be easier for Thomas. Voila, I think I'm done here. And yes, this Malta Academy is in English because Malta is in Spain, in Germany, and in France. So we are trying to do more content for all our communities in Europe. And yes, there will be a replay. I will also put the website you could find the replay after on the chat parts. And I will mute myself and disappear. So have a nice Malta Academy. See you after.
Thank you, Clémentine, and welcome everyone. This is a presentation about two concepts, first-order logic and TLA+. TLA+ uses first-order logic, so there's a meaning, a sense why I'm presenting both. This presentation does not require you to have prior knowledge in neither first-order logic or TLA+. So without further ado, let's get started. All languages have different paradigms. Like C, you can consider it procedural, Java, object-oriented, Haskell could be considered a functional language, but all have the same goal. They are built to execute on a machine. And executing code on a machine means that there might be difficulties in modeling, in predicting the behavior of the code, because you need to run the code to know the behavior of your code. Unit tests are great. Property-based testing is also a great technique, but you will always run in the limitation that your code needs to execute. Enters TLA+. TLA+ is a specification language introduced by Leslie Lamport, and it uses another paradigm, which is a logical paradigm, to model the algorithms. Leslie Lamport used them to model concurrency protocols that are very difficult to run because there are millions and millions of scenarios, and it would take a very long time to run them and to instrument them. So what does TLA+ mean? TLA+ is, T stands for temporal. It means that we will have a notion of time, a notion of discrete time that is quite intuitive. It's a succession of different steps. Logical, because it uses the first-order logic to model different scenarios. And actions, why not? I don't know exactly why action has to stand in there, but it's there. TLA plus, well, Leslie Lamport did not invent the idea of temporal logic or anything like that, but TLA plus is a very widespread language in the industry. So what we will work on is the reservation train kata. We will try to model how train can be, how seats in a train can be reserved. We will have a user that will ask the train how many seats he wants. So in this case, 2 seats. And the system would be responsible for returning him a reservation with a number and the seats that he reserved. It is a very simple model, and it will help us help me introduce a lot of the basic tools of TLA+. We will try to implement a single rule, that is, trains will have to reserve at maximum 70% of their total seat count. The idea is that, for instance, if someone does not have time to reserve and needs to take the train at the last minute, we need to offer them at least a certain amount of room so that they can go on the train. Enters first order. And yes, this is the only joke of this presentation. First order logic is not a fascistic regime. It is actually a tool of logic which helps us formalize the problems we face. First order logic has a couple of uses sets and values. Values is, for instance, A, B, the letters or the strings. They can also be the numbers, like 1 to 10 or whatever. And there are a couple of operations. Here, we're going to set coach as a set of the letters A and B. Seat number will be the set of the seat number in each coach, so 1 up to 10. So there will be 10 seats in our coaches. And seats will be a set of all the possibility of seats. Say A1 is the seat numbered A1 in the coach A, AB, A2, B1, B5, so on and so forth. In order to do that, we use the X, which is a scalar product of the seats. The expression is equivalent to, say, seat is the set of tuples A, a letter, plus the seat number. So you have A1, B1, A2, B2, etc., etc. First order logic is allows you to create relationship between the values. So here we have a predicate that says I belongs to the set 1, 2, 3, 4. TLA plus will always try to make those predicates true, meaning having I have the value 1 or 2 or 3 or 4, but not 5, 6 or 7, for instance. It describes relationship between those predicates. So we can describe the fact that if I belongs to 1 and 2, it implies that I also belongs to 1, 2, 3, because, well, if it's equal to 1, it's also 1, 2, 3 in the set 1, 2, 3, and 2 is also in the set 1, 2, 3. So you have this notion of relationship between the predicates. Here, for instance, there is this predicate that takes, so the parentheses allow you to create, to have a parameter in your predicate. And this parameter seat means that you have, say, the seat belongs to the coach. The first occurrence of the seat, the 1, so it corresponds, seat here would correspond to the tuples we've seen just above, and tuples are indexed where they're 1 index, meaning that their index starts with number 1. So seat 1 belongs to coach A and B. Well, the first part of the seat belongs to A and B, and so the little arrow means and, it's conjunction, and seats 2 belongs to 1 up to 10. So 1 dot dot 10 is the equivalent of the set 1, 2, 3, 4 up to 10 that we've seen before. So those are basic tools of first order logic.
Thomas?
Yes.
Very sorry. You have a first question from
Yes.
Clément. How does one read the symbol equals with delta on top of it?
Okay. Yes. Very good question. Thanks for pointing it out. It is a equivalence symbol. In the predicate, and this predicate shows it, you can say equal, meaning it's also a relationship. A seat can be equal to a value. So you can compare values, and the equal with the triangle above is not something to mean a comparison between values. It's an equivalence of predicates. All right, I hope I've been clear. So yeah, there's a difference between equal with a triangle and equal, because you can use equal in your predicates. So we need to distinguish those two. Thanks for the question, actually. Now, I'm going to introduce the two most powerful tools of first order logic, which is the existential operator and the universal operator. Existential operator is actually this little e, the flipped e that you have at the beginning of the predicate. And it reads very easily, there is. So you can replace in your mind this e flipped with there is. And here we can pretty much say it in English. There is a seat belonging to our set of seats, such as the dots here. The seat is equal to the tuple A1. So here what we're saying there's an existence of an element of a value that corresponds to this predicate in our set of values. So if our ensemble, well, our set seats have one such element, it will be true, otherwise false. And TLA plus will try not to get into the false state. We will see, and I hope you understand a little bit afterward. This is the existence, and you have the universal, which is the A flipped here at the beginning. The A flipped can be read for all, for every, for yes. So you can say for all seats, all seat belonging to seats, belonging to the set of seats, the conjunction up of seat, which is the predicate that we defined a bit earlier, is true. And this is as well true because we defined it as I defined it so that it is true. But all this operator allows you to define what is defines all the elements of a set. An important detail is that universal quantification, meaning when you try to define something universal about a set, does not mean that there is an existence. So if the seat set is empty, we will consider that the universal predicate is true. It means that if there's a universal, if you say for all of my elements in an empty set, it doesn't mean that there is actually an element that that respects that predicate. Sorry. So universal, existent, some Booleans expression like and belongs to, all this kind of tools allow us to, well, is used by TLA in order to describe situations. So what we'll try to do is write our first TLA plus specification. I'm just introducing another operator. Here it's the union. Union of two sets is a conjunction of all the values within those sets. So set 1, 2 union set 3 is equal to the set of 1, 2, and 3. What we will try to do is have a very basic first specification. And what we'll try is have only a single seat being reserved. The client comes and he reserves a seat, and there's only one type of reservation possible, which is the first seat. So the first specification, we will look at it in a couple of seconds, will look like that. And I want to go through a little bit of all the words here to explain you what it means exactly that we're writing here. I'm forgetting about all the details. First, what is important is the variable declaration. The variable declaration means introduces the state that we will look at every step of our specification. So here we're gonna look at the reservations of our train. Reserve will be a keyword for what will happen in a next step. So here we're describing reservation prime. The prime operator means the state, the reservations in the next step. And what we are saying here is that reservation in a next step is equal to the reservation in the current step union the first seat A1. Also, there are special keywords here, init and next. There are kind of idiomatic way of saying that. Init will be the first, the state in the first step. So what is the reservations gonna look like at the first step? And what we'll say is here, in our case, at the first step, the reservation set will be empty. So there is no reservation. Next is the operator that describes what will happen at between each steps. So TLA plus will make sure that between each steps, the next predicate is true. So reserve is true. So if we look back, reserve is we're gonna add to reservations, to the top of all the reservation, a new seat. And this will be the very first, the specification between each steps. All right, so let's go into, if I manage to, the toolbox. So here I introduce you the toolbox. It is TLA plus IDE if you want. So first, you notice that I lied a bit to you, and the presentation is written in ASCII and not the characters that I showed you. Actually, if I go into produce PDF version, well, that wasn't expected. All right, there's a problem, sorry. Actually, when you produce the PDF version, what I want to show you is that it produces the kind of presentation that I showed you with the equal, with the triangle, union being replaced by a cup, and so on and so forth. I'm sorry it doesn't work for here, but it's not really important. What's important is that there's two ways of showing, presenting TLA+. So this is a more ASCII presentation. It has the same, it's exactly the same specification that I showed you. And what we can do is create a model. I've already done that. This is some kind of configuration, and we can run the model. When we run the model, it will try to make sure that init is true and then trigger the next operations. What is nice is that it shows you how many states it has found. We will not go into it here, but what you can see is that the distinct state is 2, is equal to 2. And it's normal because in the init step, we have a first state where we have no reservation. And in the second step, we have just a single reservation of a single seat. And that is all the steps, the only kind of states that we can have. So here was a quick tip discovery of the toolbox, which is TLA plus IDE.
Thomas?
Yes.
Sorry, I'm back. Alexander says on the chat, maybe you have to add .tla to the file name to be able to produce the PDF.
Thank you for helping, but I think the problem is that I changed the name and it's somewhat there's a problem with the PDF version. I've never tried to change name before, but maybe I shouldn't have. But anyway, it's a detail. I think it's not really, we shouldn't focus on it. But thanks for the heads up. So this was a quick rundown in the toolbox, and we will go back to the toolbox as we march on we get more and more deeper in the specification. First thing we can do is, instead of reserving always the same seat, what we can ask TLA Plus is to produce a specification where it will reserve seats one at a time. This is like a very simple, reservation process, but it introduces the usage of the existence operator that I showed you before. Here we're saying that the next step, you will say that there is a seat in the number of seats, so that the reservation, this seat is added to the number of reservations. And so instead of having like 1 or 2 state, we will have a lot more state. And that is something I want to show you in the toolbox right now. So I simply wrote the existence of seat in the seats that we will add to the reservations at each steps. Again, the model I prepared And what we will see is that instead of finding a single distinct state, it will find a lot more. My computer is burning right now. As a quick, I should have said that before, but I don't know if you thought of the number of states that there is if you try to book a single seat at a time, but actually there's a lot of state because TLA Plus tries to check all of the state. For instance, reserving A1 at first and then A2, but also reserving A2 at first and then A1. So you have a lot more. There's at least 1 million steps to reserve a single seat. So here we have it finished, and it showed that it found 1 million of distinct states. And given that, we will want to introduce the invariant that I talked about in the first place. We want the train to be reserved at most 70%. For that, I will introduce another operator called union, big cap. Is that big cap? No, it's, sorry, the inverse of small cap. Anyway, and union allows us to unify a set of set. So here, for instance, we have a set of the set 1, 2, 3 and the set 1, 4. And the union of those values is 1, 2, 3, 4. Sets have unique values. You can't have the set 1, 1. Well, you can't have twice the same value in a set. And if you notice, it is also the same. This set of set is also the way reservations are implemented right now. Reservation is a set of seat. Cardinality is a simple function that allows us to count the number of elements in a set. So here 1, 2, 3 has a cardinality of 3. This is a very simple function that is very useful. So what does it mean to have 70% of train occupation? It means that we have, so here we use the cardinality of seats, the number of seats. In our configuration, there's 20 seats. That we multiply by 70, divide by 100, that's 70%. And we have something like 14 seats. What does it mean to have at most 70% of train occupation? It means that the cardinality of the union of reservation, meaning the seats that are reserved, the number of seats that are reserved, is under or equal to 70% of our train occupation. So let's try to get into the toolbox and enter this invariant. So I write the 70% train occupation as a variable, and I write what I want to enforce, the invariant that I want. Usually they are written after the init and next operation, and we say we want at all time the cardinality of union reservation less or equal to 70% of the train occupation. Here we're gonna, in the toolbox, what you can do is check the invariant. It is written down here, formulas true in every reachable state. It means that TLA Plus will check our invariant at every step, every state that it found in our specification. If we run that through, it will basically try to find all the ways that there are to book or to reserve a single seat whilst maintaining our invariant. And of course, because we're not yet limiting the number of seats that are reserved, TLA Plus finds a counterexample to our invariant. It says that the invariant is violated, and it shows us an error trace, meaning the steps that he'd gone through to find the counterexample. So here it's reserved seat A1, then seat A3, actually, and then it shows all the steps it'd gone through until the invariant was violated. So as you can notice, it doesn't have, it can be quite random sometimes. So what is written here in the error trace might not be what I show you in my illustrations. So here what it finds is basically it reserved all the seats in A, and then in B until 15 seats has been reserved. And so we have a counterexample of the invariant we try to enforce. In order to enforce the invariant, meaning to respect the invariant, we can change the reserve operation and say, when we try to reserve, the cardinality of already reserved seats need to be below 70% of the train. And we're using the conjunction operation twice. It is a bit of a TLA trigger. You can write ends at the beginning of each line. It's equivalent to not having this and just conjuncting both, but it's much more readable to have each condition in on each line. So I forgot the fixed version, the toolbox. We go in the toolbox. We write down that when we reserve, we need to be below 70% of the train occupation. And if we run the model, oops, I've been a bit too quick. We show that whilst checking the invariant, it runs just like before. But contrarily to the situation we've been before, here, it will not find a counterexample. And if it does, it means that I messed up something in my presentation. My computer is burning, and this is it. It found a million states again, but it didn't found any counterexample because we limited the reservation process. So now we can go into reserving multiple seats. Instead of reserving one seat, people can ask how many seats they want. To do that, we introduce another operator called subset. Subset will turn a set into all the possible sets it can contain. For instance, it contains the empty set, but also the set with the value 1, the set with value 2, so on and so forth, until itself, it can contain itself. So subset is an element that, well, an operation that allows you to express multiple combination of the elements. We will change the reserve operation to take a parameter, the count, which is the count that is given by the user. I want to reserve, say, 5 seats. We do not change the reserved seats condition. And what we say is that there is a combination of seats in the subset of seats All right, so let me read that correctly instead of what I said. There is a collection of seats, a set of seats in the subset of seats. So there is a combination of seats, such as the cardinality of seats is equal to the count asked by the user. So A1, and if I ask for 2 seats, it will find any subset of seats that has the same count as the user, and we will proceed to the reservation, to change the reservation process. So this reads a little bit, this is a little bit more complex. I hope you can read a little bit what it means. We will also change the next operator, because before next was simply reserving, was equivalent to reserve, but now that reserve has a parameter, we need to enter a parameter, and what we'll say is that there is a seat count between 1 and 20, in our case, where reserve is true. So if there are, so this allows us to create a situation where someone wants, say, 1 seat, and then someone wants 2 seats, and then someone wants 3 seats, and then someone asks for a single seat. And all the combinations of reservation will be tested by TLA+. So let's go in our toolbox. Again, I prepared that, otherwise it would take a bit too long. And I've changed the reserve operation. Didn't change here the condition, and I've asked to select a subset of seats so that the cardinality is equal to count, and we proceed to reservations. Now, imagine the number of the number of possible ways to reserve seats with a lot of counts. You will understand that there's a lot of state possible. If we run the model, instead of 1 million of states, I think that there's going to be a lot more states. I think that I won't run it until the end. All right. Before it went far too, well, it explored far too many combinations, at least 5 million distinct states. So that's what I'm gonna, no. So there's a lot more states that are explored by this specification, because now instead of reserving 1 seat, we can, there's also like, you can also depend, there's also the combination of how many seats you reserve, which explodes the number of states possible, but it still finds a counterexample. Here, the reservation is the reservation of the seat A3, and then there's a big reservation of seats that that creates contradiction. We have more than 70% of our train reservation. So we'll go back in the presentation, and this is what the counterexample looks like. At the first step, it reserved a single seat in the coach A, and then there was a reservation of 14 seats, and that counted up to 15 seats. I'll let you think about why it did that while I drink. So, because it's very complex, it's normal if you don't have an idea. If you have an idea, it's great. You are a genius. Because it's very difficult. I kind of explain all the things, and yeah, it's normal if you didn't find anything suspicious. Actually, what happened is during our reserve count, we kept the our old condition that the cardinality of already reserved seat is strictly below 70% of the train occupation. And then you can proceed to reservation. And this worked with one seat reservation, but now that you can book a lot of seats at the same time, it means that, for instance, you could reserve 0 seat and then reserve the whole train. If you reserve the whole train, the count of already reserved seats is 0, and so 0 is below 70% of the train occupation, and then we proceed to the reservation. So this condition is not true anymore. What we need to take account for is the count that is asked before proceeding to the reservation. We need to ask, given the cardinality of already reserved seats added to the count of newly reserved seats, this count should be below or equal to 70% of the train occupation. And this would be correct. Now, what's nice about TLA is that we can, oops, sorry, I forgot to insert. What's nice about TLA is that you simply have to fix your specification, and then I'm just going to check my invariant on the model. You just have to run the model, and it will tell you whether or not the specification was fixed. Actually, I'm not going to run through all of it because it will take far too long, so I'm just going to stop it and we will go on to the next problem. Overlapping reservations. Our specification right now is correct for the invariant that we find, but actually if you try to encode it, there is a condition that is a bit suspicious. Oops, I'm just gonna go back here. If you look into it, here I say that there's a combination of seats that we can reserve, but I have a suspicion. The suspicion is that the same seat can be reserved multiple times, because here we're not checking which kind of seat you reserve. So already reserved seats can be chosen in our new reservation. Instead of fixing directly the specification, what we'll try to do is first show that seats can indeed not be reserved once. And for that, we will first try to express in first-order logic what it means for a seat to be reserved only in a single reservation. So here is the way of doing it, and there is also another way that I won't show, but you can also use cardinality to express it. So this is left as an exercise. Yeah, this is obnoxious when I read someone say that, but what we will instead, we will express it using only the first order logic building blocks. What we will say is that for all seat, so for each individual seat, given two reservations, combination of reservation, if the seats belong to the first reservation and the seat belongs to another reservation, it means that those two reservations are equals. A bit of toolbox. Here we introduce this new invariant, seats reserved once. We express that, as I say, for all seats given to reservation, if a seat is in the to reservation, it means that two reservations are strictly equal. It implies. I put the invariance in my invariant model, and then I check the model. So hopefully it doesn't take long. Hopefully. Well, I think, yeah, here it is. Thank God it worked. Now, the error trace is really interesting. It shows that first there was the reservation of seat A1, and then on the second step, there was the reservation of seat A1 and the seat A2, which is exactly what we suspected. The seat A1 is reserved twice, and this is not something we would like. To fix that, so here is the counter example that is found. I mean, yeah, I don't know what those numbers are, but you get the idea that there's a seat that is reserved by two different colors. In order to fix that, we will introduce the set difference. So the set difference allows to subtract element from a set that belong to another set. So here is set 1, 2, 3, and when we remove the elements 3 and 4 from 1, 2, 3, we are left with 1 and 2, this set of 1 and 2. So this is an operation. Note that 4 is not a problem if an element is not in the first set. We really want the difference of the sets, and we don't want an error if there's a problem in the elements. Using that, and this will be the final specification that I show. Here we can introduce a notion of free seats. That is basically the set of seats minus the already reserved seats. And the idea is that here we will choose seats from this set of free seats. And so there will not be any overlapping left. So I won't run the model because it takes a lot of time to model that, but I hope you understand that it works. And this is it for the presentation of the specification. You can relax now. I will explain a bit what we've seen and what to do next if you want to dig into the tools. So first order logic. It is intuitive in the sense that operators like for all elements, existence, sets, and values is quite intuitive and very easy to understand. There's a déjà vu, a sense of déjà vu in those things. And the reality is math, as we teach it, already uses some of the concept of first order logic because it's an easy way of expressing math, but also expressing algorithm problems. It is powerful because you can express a lot of problems with first order logic. And actually, most of the problems you find yourself can be expressed in first order logic. The kinds of problems that you cannot express in first order logic would be things like does my specification work in 70% of the case? This is not something that works in first order logic. You will need something a bit more powerful than first order logic. But for problems that either are true or false, it's a very powerful tool. And TLA plus yields the power of first order logic. It's a very, it is intuitive because first order logic is intuitive. It doesn't add a lot more to first order logic. It only adds the temporal elements, so that steps and the description of next steps. But otherwise, it is quite, once you understand first order logic, you have a good sense, you can have a good sense of what TLA plus specifications are about. It is also easy incremental modeling. As I did in the presentation, we started with a very simple single seat reservation, and then we added constraints, invariants, and then the invariants kept on providing good information, even though our model was changing. You know, we were adding multiple seats reservation, and then we will remove the overlapping, etc., etc. And so what you write at the beginning still, well, requires small modification to work with new models. And this is very powerful, I think, for in TLA plus. And also TLA plus was built for distributed system. So let me explain. Right now, what we had is a single person asking to the train, basically, or a single node or a single element that would describe the whole reservation process. But actually, reservation process are distributed. You have a front end that has maybe cache. You have reservation service that does not do the train attribution. So you can have train attribution service that is different from the reservation service, and so you have a lot more events going on with a distributed system. And actually, instead of having one user, you can have also a lot of users. And this is kind of where TLA plus has a lot to offer, is that it can very easily describe those kind of situations. So what's next? So if you want to go further within TLA plus, I would advise you to download the toolbox and play a little bit with some tutorials, some very easy specifications. There are clock specifications, there are easy, very accessible tutorial here on the net. There is a TLA plus Google group that will answer your question very nicely. Read the book. There is Leslie Lamport wrote a book about TLA plus, and I think it's if you want to go a little bit deeper than the first tutorials, it's a very good entry point. And actually, I haven't written it, but there's also a collection of videos that are accessible. And finally, I think have fun, because I think TLA plus is a great tool to get into it. It will change your vision of algorithm and how system interacts. Thank you a lot for your attention to this, I think, very difficult talk. And if you have any question, please let me know. I will just stop the sharing so that we can have. I will go into the questions that you've asked first. So Scott Stye asks, since TLA plus model verification is CPU intensive, how common is it to run that step on more powerful machine in the cloud? I think in this, there are a lot of users in TLA plus. If you go deep in TLA plus, people use a lot of the cloud, and actually the toolbox integrates. You can very easily run your specification on AWS or things like Azure, or anyway, on the cloud. You can. There's a very the toolbox is equipped to solve this problem, and so if you have a very intensive specification, you can ask it to run even in a distributed setup. So the tooling here is really great. Although I admit I have never tested it, so sorry if I'm not an expert on that subject. Can you give us example on how you were able to apply TLA plus to real-world problem? TLA plus is already solving a lot of real-world problems, but I think that right now there's a lack of examples of, say, general public of developers type of problems. The type of problems that are solved in TLA plus, and you will find a lot of TLA plus specification in that field, is the distributed algorithms. So if you are interested in Paxos or Raft, if any of those names ring a bell to you, you will find TLA plus specification of those algorithms. It's something that is now kind of I forgot my standardized way of testing algorithm in this field, and I think I know that there are real-world example of more software general problems that are used, but I have no indication on them, and I'm really sorry about that. And that is all for the questions. I think if you have any question, you can contact me on Twitter. I will put the Twitter on in the chat. And yeah, please join the group of TLA Plus on Google Group, and people will happily answer your questions. Thank you very much for your time.
Cool. Thanks, Thomas. Thanks, Thomas, too, for your time. So, and thanks for every participant. So, for people who are interested by the replay, I will switch screens. So, it's going to be on this website in 2 or 3 weeks. And Thomas just put his Twitter on the chat. So, do not hesitate to reach him. And have a nice afternoon all, and see you soon. Thanks, Thomas.
Thanks a lot.
Bye.
See you.